Our first presentation is titled Beyond Blockchain, New Directions in Distributed Crypto by Victor Grishchenko from the Krasovskii Institute of Mathematics and Mechanics. Victor, I'll let you take the screen over from here and start sharing.
I'm not presenting any paper, so in part I'm presenting the project I'm working on. In part I'm using my paranormal powers to predict future for the next 10 years. And one may ask, why do I want to predict the future? About 10 years ago, in 2011, I read the paper by Satoshi Nakamoto, and I was working on peer-to-peer cryptographic systems. And before that, I worked on one cryptocurrency startup. So I kind of analyzed that paper and I put my opinion in writing. I posted it, it made circles, Hacker News, TechCrunch, whatever. Every year after that, I'm becoming increasingly proud of it, because most of the points I made, they even more evidently true year after year. I even mentioned that this technology is definitely not green. I mean, from the calculation, it is obvious that if it gets used at any significant scale, it will be a concern from any green point of view, that this kind of energy consumption at this kind of scale is just criminal. So at the time, I had an exchange with the top Bitcoin developer at the time. And basically, he asked how to fix these things. And basically, I had no idea. So that kept bothering me for about 10 years. So now I have a lot of ideas. I may say that the situation is slightly better. Well, on this graph, we may see the scale of the catastrophe, more or less the last 10 years, the hash rate. So we all know that Bitcoin is consuming electricity like a country, but the discussion is like which country: Denmark, Netherlands, Poland, Argentina. There are many opinions. Nobody knows for sure, but it consumes a lot. At the same time, it produces, it makes like 7 transactions a second. So I will put that into comparison. This is like the earliest electromechanical telegraphs, which was actually popular. It is a Baudot system. It is like 30 words per minute per operator, 4 operators per machine. So it is like 2 words a second. So it was slightly slower than Bitcoin. So definitely, yeah. But if you consider this machine, which is more or less the same time frame, it is a Maxim gun, and it was like 10 bullets a second. So it was faster than Bitcoin, noticeably. I must especially notice that the mechanics of a Maxim gun was modeled after a steam engine. So basically, the approach to engineering, all the engineering paradigm, it was a lot of was copycatted from steam engines all the time. So basically, so far Bitcoin is slower than steam engine level engineering. We may say that we are big fans of steampunks. So then some people say that we will introduce more sharding, and that will increase performance. Then here is the sharding. This design is from 1940s, so it is relatively modern, but it was already obsolete at the time. In case your system has less than 4 shards, then the Maxim gun is still faster than yours, most likely. That irony aside, let's think what the problem is. My understanding of the problem is like this. A blockchain is basically a linked list. I mean, if you take a regular linked list and we replace pointers with hashes, we have a blockchain, and the other way around. And linked list is a data structure which is not actually recommended for practical use because of its numerous shortcomings. For example, to reach an arbitrary point in a linked list, we need O of n iterations. We have to cryptographically speaking, if one dealing with blockchain, we have exactly the same problem. To verify some piece of history, we need to iterate the entire chain back to that point. About 10 years ago, that was Delft University. that was joint work with Arne Bakker and Delft University. We proposed a live Merkle tree. If you consider Git or typical blockchain, we have like Merkle blocks, which are connected by a linked list of references. And the idea was to use a unified live Merkle tree, which doesn't have the two parts. It is just one unified Merkle tree which grows right, and hashes in the tree are getting like filled out gradually. And this kind of construction was actually envisioned for live video, but since it was adopted by the DAT protocol, which you may know about, and it was partially borrowed in the design of BitTorrent version 2. So the good part about this design, it is extremely easy. You need a logarithmical number of steps to reach any cell. So it is like a binary search tree as a data structure. So I'm really surprised that I look at all those blockchain designs and I see that same old linked list everywhere. It introduces a lot of limitations. It restricts really the design space, and I think that is really an obsolete design. Then another problem to consider, the accumulation of cryptographic sediment. Basically, we have history of the blockchain, the transactions from people who are long dead, and all that cryptographic primitives, hashes, signatures, and everything, it accumulates indefinitely because all those primitives, they are part of the record, so they affect any later record. Basically, to make everything clean and nice, we have actually to keep that sediment forever. It is part of the record. And then the idea of monotonous crypto is to arrange primitives in a way that all primitives are generally not part of the record. So there is one-way arrow from the data to crypto primitives. And basically, we may discard all the primitives because either they're derivable or they're superseded by new primitives. As an example, we have two duck graphs, and one is a superset of another, like this one is earlier, this one is later, and they're signed by the same key. Well, under most circumstances, we can discard the earlier signature because it is the same key and all the same data was signed by the same key later. So the idea is monotonous crypto is to make crypto primitives discardable under the natural course of events. Another thing to consider, web of trust and trustless computation are kind of there is a contradiction, but it is mostly illusory. When we send something over Bitcoin, some coins to somebody, we probably expect to get something back. So there is some instant trust relationship. And overall, all that economic activity tends to happen in networks. By the way, this is a screenshot from Palantir application, some earlier version. So it naturally happens in networks, and all blockchain designs, they seem to ignore that completely. And I was just, I was very happy to hear about that the talk yesterday from the Facebook related group. That was very nice. Yes. So if we speak about human social graph of the planet, there is a small world rule that we can reach any human being on the planet in 6 handshakes or less. If you speak about computer networks, that number is probably 3 or 4, well, depending on what do you count, but it is possible to arrange really compact networks which are still based on some sort of trust relationships. So this is a big opportunity, and well, Ripple, maybe Ripple. Then, actually, the main topic of the talk, optimizing linear log. This slide I had to borrow from the next speaker. Thank you very much, by the way. So all the architectures with the linear logs, they have clear scalability limits, and big internet companies faced that like in the end of the 90s. So they're scaling it, they're optimizing it, and basically there are two ways. One is to make like industrial deployment of that linear log, like Kafka, and then separate systems, but it is hardly applicable to our case because this implies no trust boundaries. And the other way was to give up total order, give up linear log, and somehow live with eventual consistency. Hence, Amazon Dynamo, Cassandra. Cassandra is massively used at Apple. It is massively used. So all the data from iPhones and everything, it probably flows straight into Cassandra. And it has a really impressive scale of deployment. So one key problem I want to talk about, suppose that this graph depicts our blockchain, right? So we have Genesis block on the left, and we have like an entire history of the chain. So suppose we are accepting some coin as a payment, then this red dot is us accepting a coin, and the white dot is a point, if you see the yellow rhombus on the right, and the white dot when the coin was minted. If you arrange things right, then all the data that is relevant to the transaction resides in that rhombus. Like it is not like all rhombus is relevant, but all relevant data is in that rhombus. From the point it was minted to the point it is going to be accepted. So the idea is why, when I accept a coin, I have to consider the full history of every coin in the universe. That is actually a question I don't see much of talks about. Then, suppose we switch to some sort of causal partitioning. I mean, it sounds cryptic, like causal partitioning, then give up total ordering, Minkowski geometry, but in fact, we use causal partitioning when we are using Git branches. When we are using Git branches, we are using causal partitioning. It is not that noticeable because typically those branches have 99% of shared content, but still it is causal partitioning. There is one branch, there is another branch. At some point, we merge them, or maybe not. At this point, I mostly talk about the ongoing project. It is replicated object notation and drone-based storage and everything like that. Assuming we want to limit the relevant data to that yellow rhombus on the picture, then basically we have to live with a database which naturally works with causal partitioning. So it is like Git, but even worse, to say it this way, or more radical. We have data, we maybe have some shared root in the past, but the data naturally lives in different branches, and unless there is a real necessity to synchronize those branches, they stay independent. So this kind of approach, it is like more radical than Git. Another relevant model is like class 6 from 1978. It is Lamport's model of events in a distributed system, also highly relevant in this context, and obviously it happened before relation. Like for most pairs of the events in our blockchain, we are probably not really interested in the relative ordering because these are just different pieces of data. More or less, replicated object notation-based storage looks like this. It may live in different. It may have different branches. Those branches may be not merged at all. They're mergeable, but it may not be needed to merge them. Like in case of Git, eventually everything gets merged. Actually, not, because, for example, Linux kernel, it has parallel branches for new tree and maintenance tree, but nevertheless. So long living data branches, and more or less this is the situation. So in terms of chains, for each writer, for each entity, for each key, we have like separate chain, and then those transitive closures of those chains form branches, and so on and so forth. And branches also may merge. This approach to databases, it is based on the CRDT theory, conflict-free replicated data types. It is like a mathematical framework which is like 15 years old for dealing with mergeable data structures. I mean, without mergeable data structures, you cannot have branches because, I mean, it makes no sense to have branches unless you can merge them any moment. And in this particular case, if all data is RDT, you can merge them any moment. So you may keep your data in branches and merge them if that is necessary. Currently, there is one public demo of Ron systems. There are various old versions of the code on GitHub. This is a Ron wiki, which is available. It is based on Ron, so basically all the text is Ron-based storage, where every letter is operation. So on the right, you may see Ron. Basically, these are patches which are referencing each other, like which patch relates to which part of the document, and so on and so forth. So on the right is the resultant wiki page. This is the kind of storage I'm talking about, just a little demo. So thank you very much. I sincerely hope that this proof of work madness will be a thing of the past, and I really have big hope in all the directions of research I mentioned. Thank you very much.